All right. Good morning, good afternoon, or good evening, everyone. I am very honored, humbled, and excited to have with us today the one and only Dr. Eric W. Davis. Now, before I introduce Dr. Davis, he has 39 years of combined aerospace industry and academic experience in astronomy, astrophysics, advanced breakthrough space propulsion, and power engineering physics, space mission analysis and design disciplines, directed energy weapons and space propulsion, future and as well as future and transformation concepts. This includes 29 years of combined experience in scientific and technical leadership, and program office technical SME support roles and national security disciplines. He has expertise in initiating and leading advanced high-risk, high-payoff research projects for the U.S. government and aerospace industry customers. Dr. Davis also has practical experience in astronomical and spacecraft systems, instrumentation, and observational techniques with a proven record in 57 scientific publications, 45 professional presentations, and Aerospace Professional Society public policy activities. In 2019 to 2024, Dr. Davis was a senior project engineer at the Aerospace Corporation in Huntsville, Alabama, where he supported NASA, the Air Force Research Laboratory, and Office of the Secretary of Defense projects on developing spaceflight testing of space nuclear propulsion engines, as well as portable, compact space and terrestrial nuclear power systems for NASA and military applications. In 2004, all the way to 2019, he was the chief science officer and senior research physicist at EarthTech International and the Institute for Advanced Studies at Austin in Austin, Texas, where he oversaw a research portfolio that included theoretical studies and experimental testing of breakthrough energy generation and space propulsion project concepts, and provide scientific advising and oversight and conducting program tasks for classified U.S. government intelligence community programs. From 2002 to 2010, Dr. Davis was the contract principal investigator to the Air Force Research Laboratory Advanced Concepts Office at Edwards Air Force Base, California, where he supported numerous advanced space propulsion and power concept studies, development, and experimental testing. Dr. Davis earned a PhD in astrophysics in 1991 and a BSc in physics and mathematics in 1983 from the University of Arizona in Tucson, and he earned an AA in liberal arts, physics, mathematics, and aviation ground school in 1981 from Phoenix College in Phoenix, Arizona. He is a full member of the International Academy of Astronautics, fellow of the British Interplanetary Society, lifetime associate fellow of the American Institute of Aeronautics and Astronautics, and member of the New York Academy of Sciences, Directed Energy Professional Society, SPIE, American Astronomical Society, and the Association of Former Intelligence Officers. So without further ado, Dr. Davis, thank you so very much for being here today.
Oh, thank you for inviting me. I'm happy to be here.
Thank you. Well, let's just hit it right off with the first question. I have a handful here for the audience to enjoy. So the first question is, where do you think, to what you can speak on, where do you think UAPs and their potential occupants originate from? For instance, are we dealing with time-traveling humans, interdimensional beings of some form, species from another planet, beings that have dug themselves perhaps into the interior of the Earth that maybe pop their head up every once in a while, or are we dealing with a mixed bag here, or what do you think?
It's hard to say. There's a lot of hypotheses, rival hypotheses, that have been circulating for many years. Hal Puthoff has the ultra-terrestrial hypothesis, which embraces a lot of those, or a subset of those possibilities that you mentioned. A favorite of many people, including Dr. Michael Masters, is future time-traveling humans that are coming back into our present, and apparently their presence here is to explore the state of our development, our civilization, and I'm guessing that he really hasn't said anything about UAP craft per se. That I recall. I haven't read the book that he published many years ago, but I've heard from many people, and from the synopsis I've read, it's very good. So what I was getting at is I don't know whether he's claiming that the UAP craft that have been observed are in fact the time machines themselves, or whether there's a time machine that brings the craft back and they hop in their little sports craft and fly around. So it's hard to say, but I have no idea. There have been decades of uh, both classified and unclassified rumors within the Department of Defense and intelligence community that that the U.S. government had been in contact with UAP aliens. One of Jacques Vallée's favorite terms for them is UFOnauts.
Okay.
So yeah, he called them UFOnauts. So I'll use that because that's easy, and it's easy to understand. Like astronauts, you have UFOnauts.
Right.
So there's been the rumor that the United States government had some contact with the UFOnauts, and I'm not going to get into the deep aspects of those because that could take a lot longer than you have time for during this interview. So,
Sure.
so that information implies that the government might know something. It suggests that the government might know something about those UFOnauts and their origin, but I've not been able to crack that egg myself. Um, so
Got you.
any speculation is good as the next one. You'll have the search for extraterrestrial intelligence and contact with extraterrestrial intelligence communities who assert the principle of mediocrity, which is the foundational principle of SETI, that it's physically impossible to do interstellar travel in the galaxy given our human known advanced space propulsion technologies, both developed and, well, let's say that, not developed, but both theoretically designed, and some had been developed, like the rover Nerva nuclear rocket engine program would be for the Mars missions back that were going to support the post-Apollo Mars missions during the 1970s that Nixon canceled in '73. And if nuclear technology in the way of nuclear rocket propulsion had been allowed to proceed further and evolve from that era, we would have had advanced enough nuclear propulsion to stage precursor interstellar flight. So nuclear precursor flights are definitely possible
Right.
using nuclear fission. Now, the rover Nerva program used fission reactors for the uh, heating element, I will call it, or the hot
Right.
rock that you're going to pass hydrogen propellant through and around to heat that up in order to produce thrust out the rear, through the exhaust nozzle. Okay, well, there's also nuclear fusion propulsion using a fusion reactor that can heat up a plasma, and you'll exhaust out that hot plasma through a magnetic nozzle, and that'll produce thrust. So that's. Oh, I'm sorry about that. I'm holding my iPhone here,
No, no problem.
and so that certainly is two forms of nuclear propulsion. A third is it really behooves me that in the space propulsion arena, we call matter-antimatter annihilation rockets one of the three categories of nuclear propulsion. Well, matter and antimatter are not nuclear, they're elementary particles. But they can involve the annihilation of atoms and anti-atoms and molecules and anti-molecules. But still, it's not a true nuclear. It's an elementary particle process more than anything else. But they just lump it together with nuclear fission and nuclear fusion propulsion.
Got
Okay,
you.
so those are the three things that could implement interstellar travel, and the only problem with that still is that the distances are so great, and you are not guaranteed to reach your destinations within a human lifetime unless you propel yourself at relativistic speeds. And then you take advantage of the time dilation and space contraction elements of special relativity to drastically shorten the distance and a time of flight for the spacecraft crew. And so that demands huge amounts of energy.
Right.
So what that implies is that you're going to have to carry propellant just to transport the propellant as well as the spacecraft and its crew.
Right.
So that's because of the rocket equation. And the relativistic rocket equation is even a little bit more complicated than the traditional Newtonian rocket equation. So you really are paying a penalty in relativistic mass the faster you go toward the speed of light, because your mass begins to drastically swing upwards in value compared to a straight up Newtonian uh, mass fraction in the
Right.
exponential term of the rocket equation in the Newtonian rocket equation. So this is where they come to the SETI folks and CETI folks is is that they're pointing that out as the reason why we can't physically travel through interstellar space. First of all, the energy required for the propulsion system is greater than the amount of energy that the United States produces in electrical power generation or consumes in electrical power generation. It's the
Wow.
same number.
Wow.
So it's hundreds of times greater. So we don't have a technology, either nuclear fission, fusion, or matter-antimatter annihilation, that can meet those that power requirement, and the fuel required and I'm talking about at present day.
Right.
So the fuel required to feed those propulsion systems is going to be huge. It's going to be relativistically huge because you're going to need to go near the speed of light in order to take effective time dilation so that your crew could reach its destination star within a human lifetime. And if you could get it within 10 years or just a few years, that'd be wonderful. But even, more than a couple of years of space flight is really hazardous to human health, as we already know from the International Space Station astronauts who've been experiencing a variety of physical degradations, bone density, muscle mass, imbalance issues, and vision problems as well, over the course of their mission time in orbit.
Right now,
So
if I can
so
ask,
I
sure.
so hang on a second. So where was I going? Let's see. I had a point in that. So basically, that's the study principle of mediocrity, is that there's no technology out there that an alien race could deploy to get to the Earth, because they'll suffer the same problems getting here that we will have going to their location. And so it just makes it energetically prohibitive. Propellant wise, it's prohibitive. Technologically, it may not be prohibitive. It just takes time, years of evolution of the technology, but it'll be costly. So cost is another factor in there.
Right.
And so the swap of these things are going to be terrible. Swap is size, weight, and power
Right.
in space exploration. So those are going to be really prohibitive for interstellar flight. But a sufficiently advanced race can overcome those things. So it's just hard to say whether UFOnauts, you're coming from another planet by using advanced space propulsion technologies like what we envision,
Right.
or even I talked about the three nuclear. What about beamed energy or directed energy propulsion using lasers? I
Right.
haven't even talked about that, but you've got to project that laser beam out across interstellar space to some point. You don't have to just accelerate it up to a fraction of the speed of light. You could just run the beam from the planet for minutes or maybe hours, and then you're done.
Right.
The craft is rapidly accelerated up to cruise velocity, but then you've got to decelerate it. And then
Right.
if you're going to turn around and come back home again, you're going to have a laser array on the exoplanet orbiting the star that you're visiting. And what are you going to do? You're going to take a giant array of lasers with you.
Right.
That just increases the swap of your spacecraft.
Right.
So the only other possibility that the SETI community did not want to consider is faster than light propulsion, because at the time that the principle of mediocrity was explicated, warp drive and traversable wormholes were not discovered from Einstein's general theory of relativity. Not until 1985 through 88 for the traversable wormhole, and 1994 for Alcubierre's warp drive.
Got you. Well, thank you. Well, speaking of which, since we're on the UAP topic, I would like to follow up before I get into the more scientific questions with asking you, to your knowledge, whether you can speak on a personal experience or what you've heard or pure theory. How integral of a role does psychokinesis or telekinesis play in UAP interactions, from what you are familiar with?
What I'm familiar with from experience and from the published literature, from scientists I respect, not from experiencers.
Right.
Experiencers are kind of a subjective situation you can't really calibrate.
Right.
So I'd go with Jacques Vallée's work. Telepathy is a major component of UAP interactions with humans. I just don't I don't see a lot of TK and PK. It certainly does make an appearance in some reported cases. I don't think it's the primary component of psychic interaction between humans, or maybe the psychic characteristic of UAP phenomenon in general. They're certainly there, but it seems that telepathy seems the more predominant human potential that comes across in any kind of an encounter.
Got you.
So yeah,
Got you.
that's about
Okay.
all I can say on that.
Well, to that point, I wanted to ask, is there ever a scenario that you are aware of in which would justify a United States president not being read into an SAP or waived unacknowledged SAP? Or would the president have to be given access no matter what if they demanded it?
A president can certainly demand access because he's the chief executive of the United States government. So, and then he's the commander in chief of the military of the armed forces. So,
Right.
so he can demand it and he can get it, but he has to know about it. If he doesn't know about it, he won't know that he could demand it. Demand being
Ah,
briefed or read into it.
so in other
Okay,
words, yeah, yeah,
so in other words, but okay, so on the other hand, during my investigations into the waived unacknowledged special access programs that have had the crash retrieval reverse engineering programs going on since at least 1944, with the
right,
recovery of the Italian of the craft that crashed in Italy in 1933. The United States Army recovered that in 1944. So after the Allied invasion of Italy to drive the Third Reich out of Italy.
right,
Um, so uh, um, so basically, my investigations into that during the NIDS era, when I worked for Bob Bigelow at the National Institute for Discovery Science, is that a source that I developed at one of the legacy aerospace companies had mentioned that presidents are not deliberately, routinely briefed upon entering office on the UAP phenomenon.
right.
Um, and whether the program managers of those programs desire to brief them depends upon a level of trust.
Mhm.
And the issue that came up with these programs is that it is a matter of what determines whether they will brief a U.S. president on the existence of UAP crash retrieval programs is whether they trust the president politically at a political level with the information. So if they don't trust a president to handle the information correctly, they will not go out of their way to offer or seek an invitation to give a briefing. Um, and if they do, then they will do the opposite. They will pass information up through their chain of command and hope for a positive response that the White House will want them to give a briefing on the topic. So it's a matter of political trust. Oh,
Right,
that's only half its character too. So it's
right,
political and character.
right.
So it's a trust issue based on the character of the president as well as the political aspect that surrounds that president's his behavior as a representative of his party.
Got you.
It's what I'm saying. So
So in
not every
other words,
president has been briefed.
Okay, so in other words, if there was a president, and I'm not trying to, for the audience, I'm not trying to allude to any one individual, but if there was a president that just, yapped out everything that was told to him or her, they would likely not be briefed on these type of programs.
Yeah. Well, let me give you an example, a well-known example. During of what happens when a president is briefed on on a special access program, which was the SR-71 aircraft development program back in the late. It actually began as another aircraft development program name called the A10, I think it was, or the A12. I can't remember which, but they had the same configuration. That craft had the same configuration as the SR-71. So uh, so up until during the early 60s, Kennedy got assassinated, and then LBJ was sworn in as the new president of the United States. So now LBJ has completed Kennedy's term, and he's now running for election for his first full 4-year term as president. What he did is he was briefed as vice president of the United States on the SR-71 program. And so he's giving campaign speeches around the country. And during one campaign speech, he was trying to articulate his defense bona fides in order to appease the people who didn't see him, strong on defense. And my gosh, he's running the Vietnam War.
Right.
So I don't know how strong, how weak that could be on defense, but he's running
Right.
the Vietnam War. So he wanted to mentally come up with an example of what he's doing to give the Defense Department new types of tools to battle the Soviet Union, and he just blurted out that we were developing the SR-71 program, and he just
Oh,
did it. So technically, he has all the power to automatically declassify any level of classified program, regardless of whether it's a confidential level all the way up to top secret and all the way to top secret or secret sensitive compartmentalized information, or secret and top secret special access programs. And I don't know that I've ever heard of a secret special access program, but I know that there are top secret special access programs. Okay, so all I'm saying is that this was a special access program back in those days,
right.
and he just blurted it out. And so basically, by blurting it out, he automatically used his power without consciously realizing it to declassify the SR-71 by blurting it out. Well, he didn't go, he didn't go all the way that far. What I'm just telling you what the implication is. He
Right.
declassified its existence. That's what he really declassified. Not the content, not the
Right.
aircraft configuration, propulsion, or its operational design, or its operational modes that it's designed for, and so forth. What he did is he just blurted out the existence of the program, so he declassified it that way.
Wow.
And so he didn't intend to do that, but that's what he did.
Wow.
Let me walk that back. We don't know that he didn't intend to do that. He did do it. He did
He
intend
did,
to do
right.
it. So yeah,
Right,
he did
right.
do it.
Wow.
Okay,
Okay.
so
Well,
he used the SR-71's existence, the program, to boost his campaign prospects. His
right.
profile among his voters.
Got you. Wow. Well, thank you for that immense insight. The next question I have, and the following questions will be more scientifically oriented, but because I know with some of these questions here, a lot of people have been having discussions about some of the concepts I'm about to bring up here. So do you think that the creation of an experimentally verifiable magnetic monopole is something that may be achievable in the near or distant future? I know that there's been discussion of things like Dirac monopoles that Paul Dirac postulated theoretically. But do you think experimentally this is feasible in any capacity now or maybe 50 years from now?
We've already gone more than 50 years looking for the Dirac monopole and haven't found it.
Right.
So I don't think it's going to happen.
Got you.
I don't think any experiment is going to discover it. There have been talk of theoretical studies done that in the published literature,
Right.
that there are in semiconductor materials, there are quasi particles that have been predicted to have the properties of a Dirac monopole, but that's not a real free elementary particle out in free space moving around. It's a quasi particle, which means it is manifested. It is not an original particle. It's a manifestation of the collective action of electrons, and potentially electrons coupled to photons in a semiconductor system.
Got
That's called the condensed matter state. So there are condensed matter theory predictions that there is collective electron and maybe phonon, coupled electron phonon, or phonon photon, that kind of thing. those kind of activities that go on in condensed matter that they predict would have the behavior and properties of a Dirac magnetic monopole.
Right.
And so far, I thought I saw a paper where somebody said that they had discovered it, but I didn't see it go forward. So I think maybe the discovery was premature and didn't have the proper systematic and statistical analysis to validate the claim. So
Gotcha.
it probably didn't go forward. But I know there have been condensed matter theory publications predicting that. There have been other predictions on other types of particles, like Weyl particles, WEYL,
Right.
and Majorana particles, et cetera, et cetera. So we don't
Gotcha.
see them in elementary particle accelerators, particle collisions, colliders, and things like that. We only see predictions of those in condensed matter states.
Got you. Thank you. Well, the next.
I just don't have any hope that they're going to discover a single magnetic monopole. Dirac's theory is very good. I mean, it self-consistency dictates that you would have a magnetic monopole. And physicists have looked at the upper bound. What would the upper bound be? No, I think it'd be a lower bound. What would the lower bound be for the existence of the number of magnetic monopoles in the universe? And at least one could exist, but nobody's, where is it? If
Right.
one
Right.
could exist, we don't know where the hell it is. Nobody's been able to discover it. Obviously, you can't make it in an elementary particle collision. It's not a byproduct of radioactive decay. It's not a byproduct of nuclear fission or fusion. And it's certainly not a byproduct of matter-antimatter annihilation. And it's not a byproduct of quark gluon plasmas or any of that stuff. It's
Got.
just, it's a very basic elementary quantum calculation that Dirac did for quantized electric charge. And by symmetry, you would have the quantized magnetic charge, the
Right.
monopole. And unfortunately, we see quantized electric charges everywhere, but shoot, the magnetic monopole is a ghost.
Right, right. Well, speaking of such, this question will probably be one of the more controversial ones, given how much misinformation and potential, perhaps legitimacy there is out there. Which again, I don't know, which is why I'm asking you here. But is there any truth to any kind to the notion of some type of what have been called longitudinal scalar waves existing? These have been rumored to exist within alternative scientific communities. And so, is there any way of proving or disproving this concept, or do you think this is entirely nonsensical?
Okay, waves of what?
Specifically, electromagnetic and sound waves.
Oh, well, sound waves are longitudinal,
Got
and the P waves or primary waves of earthquakes are also longitudinal.
got
Okay,
you.
and there are ultrasonic waves that are longitudinal. Okay, but electromagnetic waves, there's no such thing as an electromagnetic scalar wave that's longitudinal because the electromagnetic field is the vector field. And
Got you.
so it will not have a scalar component. And also, Gauss's laws apply to the electric and magnetic fields in free space,
Right.
which is what electromagnetic fields propagate through free space, right? And there's no electric charge present or current present. Well, in free space, the propagation of the electric and magnetic field is strictly transverse electric and magnetic field components, which means they are oscillating. Those fields are oscillating perpendicular to the direction of the wave's propagation. And that's because of the vector nature of the electric and magnetic field. Now, Gauss's law, I didn't finish that thought there. Gauss's law dictates that for that electromagnetic radiation propagating through free space with no charges present, the divergence of the electric field is zero and the divergence of the magnetic field is zero. That's a mathematical condition that dictates that any longitudinal vector component doesn't exist.
Got you. Okay. Thank
There
you.
are very, very specific, rare cases of plasmas, electric fields in plasmas, and near fields in antenna theory, where there can be a brief longitudinal component of the electromagnetic field, but it's rare. It's rarely seen. It's very short range. In other words, it's only going to be a couple of wavelengths, and then there's no phenomenon that propagates. It doesn't propagate beyond the near field condition. The near field condition, if I remember right, if I remember right, is that the wavelength is smaller than the dimension of the object that's emitting the wave.
Got you. Okay,
Okay.
perfect. Thank you for that clarification.
Yeah,
Um,
but
yeah,
yeah, so I think that's about all I can put on that one.
thank you. Yes, of course. Speaking of theoretical physics, physicists or physics itself, I would like to ask, what is the biggest issue that you personally take with regards to the current field of theoretical physics? And what I mean by that is, do you think some physicists focus far too much on theories to the point where by the time they're done with their theories, there's no way to actually engineer their theories? Or do you think that by going in deep into theory is needed for long-term projections of what could be engineered in, say, 200 years from now, for example?
Uh, okay, that's kind of a roundabout way of saying the scientific method is working fine.
Right, right, right,
Okay,
right, yeah.
okay, theorists are just doing that. They're working with the hypothesis based on either empirical evidence that exists. Somebody made some observations somewhere of consistent phenomenon, wrote it, recorded it, recorded it somewhere, published it somewhere, and nobody's got an explanation for it. So a hypothesis would be formed to explain it. So you
Got
have a phenomenon being observed, and you need to form a hypothesis to explain it. So that's your theory. So you do. So you do. We're going to have to. Uh, we're going to have to redundantly use the word theory and theoretical calculations here. Okay,
got
so you're going to form a hypothesis by deriving a theoretical description of the empirical data.
got
So you have an equation now that you can use to make calculation. You've got an equation, you put its boundary conditions together, or you define boundary conditions for your equation. And so when you look at the empirical evidence that you're trying to describe using that equation, you're going to put the numbers in the boundary conditions of the conditions under which that phenomenon was observed. That'll be a boundary condition. You'll stick that in the equation and you'll crank it through, and mathematically you should get a prediction from that equation that matches every one of those empirical data points.
got you.
So if that happens, you have a theory.
Right,
The
right,
equation is now a theory. So you're going to be saying, well, this theoretical phenomenon that I have invoked to form my hypothesis is what's behind this long list of empirical evidence or empirical observations that have been reported in the literature on phenomenon XYZ. So I came up with this equation. I figured out under what its boundary conditions are under the conditions of the observations that were made to observe those XYZ data points. And then so now I'm going to see if my equation is correct by putting those conditions into the equation and see if the equation, my theoretical equation, will predict every one of those observed data points. And
got
so when that happens, and that's a yes, in other words, you've got a yes no question. If you've got a yes, you have a theory.
right,
Okay, now you've got to continue cranky. Now you've got your theory. So the scientific method says, okay, so you have a theory. You've been able to predict or reproduce observed phenomenon using your theory equation.
right,
And you've also fundamentally explained what the phenomenon is using your theory equation. So not only did you have a theory equation, but you also had to make assumptions, right? In
right,
order to come up with your theory equation, you often have to make guesses, good assumptions, and they've got to be self-consistent with the equation and with the phenomenon being observed. They can't be half-assed chaotic assumptions.
right,
They've got to be self-consistent with what you're doing, with the whole big picture. So if it all works, then you have a theory, but you're not done there. You now have a description of the phenomenon theoretically. You have a theoretical equation, and you can predict it. Okay,
right,
that's what the scientific method says you have to do. Now
right,
your next step is you got to keep using that equation because other people out there are going to are going to continue publishing papers discovering more of that phenomenon or new aspects of that phenomenon that have not been seen before or
right,
published before. So now all of a sudden you got a new tranche of papers getting published reporting uh, phenomenon X1, Y1, Z1, and phenomenon X2, Y2, Z2. It's all the same phenomenon, but it's under different conditions. And now you're getting different types of data. Does your equation predict it? So you got to use the conditions for those new sub 1, sub 2, XYZ discoveries and see if you can predict them.
Gotcha.
Okay, so if you do, if your equation does, your theory is solid. However, if your equation fails to predict, reproduce, in other words,
Right.
reproduce theoretically from the equation itself what has just been reported, then the theory is wrong. There's something wrong with the theory. You have to go back and mess with it to figure out if you're missing something and if you can fix the equation. If you figure out what you're missing, can you fix your equation and then start over again to see if you can predict that phenomenon.
Now,
And that's one side of it. The other side of it is you want to use your equation to make predictions that haven't been discovered yet.
right, right, right,
That's the other thing, right?
right,
So now you've got that equation. People are saying, well, I've got phenomenon XYZ, X1, Y1, Z1,
right,
X2, Y2, Z2. Now
right,
you want to be using your equation. You want to predict X3, Y3, Z3,
right.
X4, Y4, Z4, and so on. And once you make those predictions of something that hasn't been observed yet, you have to sit back, you have to publish that, sit back and wait for the experimentalists to observe it in order to confirm your theory. And if they do, hey, your theory is more universal than you realized. It's widely used. It's widely applicable to that phenomenon that you have explicated in the foundation of your theoretical equation. Um, it's the XYZ theory of phenomenon. It could be
Yes.
a new fundamental force theory or
Right.
fundamental field theory. Yeah. So
Got you.
that's really what you say. That's so
Right.
theorists work in like physicists, they work on theory development, and the theory development actually runs into brick walls. Let me give you some brick walls. Quantum gravity.
Right. Right. Right.
Quantum gravity is your big freaking brick wall
Yeah.
because you cannot. There are several incarnations of quantum gravity. Quantum loop gravity. There is quantum superstring theory. There's D-brane theory. There's the holographic universe theory, et cetera, et cetera, et cetera. Everybody's got a favorite. Oh, there's canonical quantization of gravity where you use the traditional Hamiltonian uh, for the gravitational field. You define its phase space coordinates, which are basically position and momentum coordinates. And so you crank it through. Can you quantize that? Just like you did with quantum theory, where you quantize an electron using the
Right.
Hamiltonian theory, or a photon using Hamiltonian theory, et cetera, et cetera. Can you quantize gravity by the Hamiltonian canonical, or I should say canonical Hamiltonian approach? Okay,
Right.
so you got all the and there's semi-classical quantum gravity where you leave the Einstein tensor on the left side of Einstein's general relativity field equations classical, which is constructed of the Riemann curvature tensor minus one half times the Ricci scalar times the metric tensor, and that's equal to the Einstein coupling constant or coefficient multiplied by the stress energy tensor. But the stress energy tensor represents the properties of the matter that creates the space-time curvature on the left side, the Ricci scalar curvature and the Ricci tensor curvature,
Right.
and so that's quantum matter. We all, Einstein developed his field classically in that you'll have classical forms of bulk matter, and you'll create classical curved space-time phenomenon out of which Newton's law of gravity will fall out of in the low energy, low speed limit of of that of that of that
Gotcha.
regime. And so, but semi-classical quantum gravity says, let's quantize the matter source. Hell, matter's all made out of quantum stuff anyway,
Right.
right? And it is. It's
Right.
all elementary particles bound together by the interaction forces between elementary particles.
Right.
So we're going to quantize the stress energy tensor, but we're not quantizing the Einstein tensor. So that's why it's called semi-classical
Gotcha.
quantum gravity. Okay, so you have all the different types,
Right.
and the fact of the matter is, we don't get solid answers. Prediction. Quantum superstring theory hasn't been able to make solid prediction. In fact, the one prediction it makes is that that to predict the universe that we are in and all the matter and forces of nature, including gravitational curvature, warp space time, and all that. Um, there's a solution space of 10 to the 500
Whoa.
solutions. So
Oh.
the solution space has 10 to the 500 solutions in it.
Right.
That'll take us longer than the age of the universe to calculate that using I don't know, we could probably imagine supercomputers a million years in advance of ours now, and it'll still take them longer than the age, I should say, the age of the universe, longer than the current age of the universe to calculate every single one of those 10 to the 500 solutions and
Right.
figure out which of those approximates or exactly equals our currently observed universe. And
Wow.
so then they went to alternative methodologies to reduce that down to something on the order of and I'm not going to get into all that. That's really
Sure.
complicated.
Sure.
So they found some procedures by which they could reduce that solution space down to 10 to the 11 or 12 or 13. I've heard 10 to the 15 solutions.
Mm.
And now you bring it down to the level of where probably your most advanced supercomputer, high performing clusters and parallel systems can compute. And now I'm not saying they could do it in a matter of minutes or hours or days. The computations could actually take just a few years. It's predicted that they would take 5 to 10 years or within that ballpark.
Got you.
So, okay.
Got you.
So this is the thing about those theories. They're attempting to quantize gravity. And the problem is the theories cannot predict any phenomenon that we can observe. And
Right.
that's why the grind keeps going and going and going. Oh, there's Roger Penrose's twister theory. That
Right.
was going to be his version of unifying gravity with the other forces of nature by defining twisters. And I'm not going to get into that. That's also super geometric and complicated. So the grind goes on because this is a tough mathematical problem. It's mostly a combination of mathematics, geometry, and topology.
Got
And topology means the shape of space manifold. And we
right.
live in a space-time manifold, so we have a topology of space-time. So that's all these guys can do.
Right.
They have based their entire physics careers as theoretical physicists on solving these equations from superstring theory, loop quantum gravity theory, and blah, 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 and all the other ones. And they're trying to solve the problem of being able to make testable predictions.
Right.
And so that goes on and on and on. And it's very difficult. That's a very
Yeah.
difficult area. It was really hard to unify the electromagnetic force with the weak nuclear force.
Right.
That took quite a bit of time. I don't remember what the length of time is, but Steven Weinberg and Abdus did it independently in the 1960s, and they actually unified those two fundamental forces into a single fundamental force called electroweak theory, or the electroweak force, where it was demonstrated that the weak nuclear force of radioactive decay and quark particle decay are two sides of the same unified force, the electroweak force.
Right.
And in fact, the weak force is constructed of quantum wave function basis states that are photons. So the photons in electromagnetic field form what's called the quantum basis state. I'm not going to get into all that,
Right.
but that's what it is. We can compose a weak force describing its massive vector bosons that transmit the weak force in terms of the photons of the electromagnetic field, the quantum electromagnetic field.
Right.
So electroweak is really not Maxwell's theory; it's quantum electrodynamics, which Richard Feynman won the Nobel Prize for. So he quantized electrodynamics, or Maxwell's equations. So he quantized that, and that's called QED theory, quantum electrodynamics. And
Right.
so Abdus and Steven Weinberg unified that with the weak nuclear force, and they said, aha, there's a symmetry principle involved. And when you reinsert the symmetry principle, you unify the two forces as one. But we know that that symmetry got broken during the evolution of the universe. So it got broken. And when you break it, you create two forces out of one.
Right.
Yeah, there you go.
Right.
And yeah. And by the way, the photon is, so you have the positive and negative electrically charged W vector boson for the weak. That's the weak force decay boson. Then you have the neutral Z boson. It's a vector boson, so it's neutral charge, no charge. It's Z to the zero,
Got
whereas the W would have a plus sign, and the upper index and a minus sign in the upper index for both the electric charges of it. They're all three are massive, but the photon is the fourth one. That's the massless vector boson. Vector means they all have spin one. So everything that propagates the electrodynamic force or electromagnetic force and the weak force are spin one particles, which means they have only two polarization states, transverse to the direction of propagation of the field, just like the electromagnetic radiation.
Got you. Well,
Yeah.
thank
So
yeah.
that's the difficulty. Hey, quark theory. Quark theory took a long time too. It
Right.
took decades, but it didn't take as long as what's going on right now with quantum gravity. Um, so I could say quantum gravity really got started. People might say, well, Einstein was trying to unify gravity with the other forces of nature. We'll say that's when it began, but
Sure.
he wasn't quantizing anything then. Then it kind of died off after he died, and then kind of started resurrecting itself slowly during the 1960s. And it really took off when Stephen Hawking made his grand appearance on the scene in the 1970s. And
Got
other people besides Hawking, not just him, Larry Ford, Don Page, oh gosh, there's a whole list of people I can't think of right off the top of my head who started that whole genre of quantum gravity exploration. But anyway, quantum chromodynamics is the field theory for quarks and gluons. Okay,
right.
so that began the same way quantum electrodynamics did, the same way electromagnetism did. Electricity and magnetism separately did, and the same way the weak force did. It was all experimental empirical observations. So they're seeing all these unusual particles coming out of elementary particle colliders or particle accelerator experiments is what I mean to say.
Right.
And that led to the discovery of things called partons, very complicated particles coming out of they're in the form of a jet that's coming out of the collision region between two counter propagating beams of elementary particles that are smashing into each other in a collider or
Right.
accelerator. I'll call them a collider. Everybody's got a different name for those
Sure. Sure.
for those machines. And so one thing led to another, and they finally came down to understanding the empirical properties of these partons, and that's when people started talking about quarks. And
Ah.
quarks emerged as a fundamental, as a proposal for a fundamental particle as fundamental as electrons, electrically charged, but there's a new symmetry. There's a whole new symmetry overlaid on top of that called the color force. And the color
Right.
force, there's three color forces: red, blue, and green. And that's a whole different. They call that a color charge. So quarks and gluons have color charge on them. Now gluons are not electrically charged; they're electrically neutral, like photons are.
Right.
They're spin one, just like a photon. They have one spin, which means they're a vector boson, and their wave properties are transverse to the direction, or their polarization their vibrational modes are transverse to the direction of propagation of the force, and et cetera, et cetera. So, what evolved out of years of theoretical tinkering and experimental data to drive the theoretical tinkering and the hypotheses, which leads to the first equation, came the result of the quantum chromodynamic theory. And the quantum chromodynamic theory, surprisingly, or surprise, surprise, looks so similar to quantum electrodynamics, with the exception that it's going to have a higher level or a higher lower order of field theory attached to it than the regular electromagnetic field, because you not only have electric charges, positive and negative, but you have color charges. So now you're adding a new layer on top of the field, the particles, and so forth. So
Got you. Well,
yeah, those things take time. Those things
yeah.
take time. It takes, and so they could drag on for decades with a successful conclusion. But once you successfully conclude any theoretical development that successfully predicts phenomenon that you've already observed, and it
Right.
predicts phenomenon that you haven't observed, but people are now starting to report observing, observational evidence to support the prediction, et cetera, et cetera. So now you apply the theory. So
Right.
once you're done, now you have to apply it. What can you do with it? So
Right.
now that you know what it is, what can you do with it? Are there other experiments you want to do to pick and probe at that theory to see where it breaks down? Or maybe your theory is now predicting new phenomenon that you didn't know it would predict. You know,
Right.
you're pushing the envelope of the equation further and further. You're coming up with new predictions. So that means you got to go to the colliders and start colliding heavy particles in accordance with the boundary conditions that help push your theory equation to the envelope in hopes that you'll see the new phenomenon that the equation is predicting.
Got you. Well,
Yeah,
thank you so much for that. That was amazing. The next question I wanted to ask, and again, another bit of a controversial question or a topic, so to speak, is this concept of what's been called inertial mass reduction. The idea that an object would begin to lose its mass under specific
yeah.
conditions. Is there any feasibility or any truth to that in any capacity?
No, that's meaningless. That's
Okay.
absolutely meaningless.
Okay.
Let me give you a very a strong point of clarity on mass.
Sure. Sure.
We have gravitational mass, inertial mass, and there's a third one I can't think of. Maybe there isn't. I'm trying to think, but anyway, it's been assumed in physics, and under the self-consistency of the laws of physics, the two are equal. You
Okay.
start with the assumption that they're equal, but then self-consistency of the different laws of physics supports that equality. Okay,
Right.
so what do we know about inertia? Well, okay, you've got Einstein, you've got Newton's second law of mechanics of motion,
Right.
and that means that force is proportional to a rapid change in motion, being acceleration.
Right.
So, what's the proportionality constant? In other words, things that are accelerating are only accelerating under the influence of an externally applied force, right?
Right. Right.
All right, well, what's the proportionality constant between them? Well, the force is in units of newtons, and acceleration is units of meters per second squared, or length per time squared. And so the proportionality constant has, no, wait a minute. Yes, correct. The proportionality constant has to get rid of one of those units on one side of the equation in order for the dimensional units of the results of the one side equal the other side. Okay, so here's how you write it out. F is proportional to A. External force is proportional, A being acceleration, a second order rate of change of motion. So the first rate of change of motion is speed or velocity, with and speed with direction gives you velocity, and velocity is a vector. The components of vectors are magnitude and direction.
Right.
So for velocity, speed is the magnitude, and direction is some angle or azimuth with respect to a reference frame that you're moving toward. And so then the rate of change of velocity is acceleration. That too is a
Right.
vector with a magnitude and a direction. All right.
Right.
Well, but the units of force are in MKS units or SI units is newtons.
Right.
Okay. So how do you turn meters per second squared into freaking newtons? Well, what is a newton? A newton is actually defined to be kilograms meters per second squared. So there you go. You're missing a factor of a kilogram. And you're going to multiply that by the acceleration dimensions, meters per second squared. That gives you newtons. So,
Right.
so that's what the proportionality constant must be. It must be the mass in units of kilogram multiplied by the acceleration in units of meters per second squared. And the combination of those gives you the definition of a Newton. Okay, so what is inertia? It's a resistance to a change in motion, right?
Right.
How do you reduce that?
Right. I see
How
what
do you
you're saying. I see what you're
how
saying.
how do you reduce inertia or modify inertia? It's a resistance to a change in motion, which we quantify as a proportionality constant between an external force and an acceleration. So what are you reducing? Um,
Right.
the only thing you
Right.
can reduce is acceleration or force. That's what will reduce. That's what, or you can increase it. That's what will change your F equals ma. But you can't alter the proportionality constant. It's a constant for that very reason. It doesn't vary. It's not a function of energy. It's not a function of time, distance. It's not a function of gravity, gravitational force. It's not a function of your grandmother living next door to you or not. And
Got you.
so, okay,
Got you.
so now that's just one half of the issue. The other half of the issue is we know from quantum chromodynamics and empirical evidence of the relativistic heavy ion collider at Brookhaven National Lab at Long Island, New York, that all of the evidence shows, after decades of using the RHIC experiments to create quark gluon plasmas,
Right.
and that's what it's designed for.
Right.
You're colliding everything from protons, which are the nuclei of hydrogen atoms. So it's basically just a hydrogen ion,
Right.
because hydrogen atoms only have one electron. If you remove the electron, you got the proton left. So that's an ion.
Right.
And it just so happens that the hydrogen ion is a proton. Okay, so you got that. Then you've got gold, silver, lead, atom, nuclei. Then, so what you do is you make those ions, you strip all their electrons off, and all you have are just the nuclei of each of those atoms. So
Right.
let's see, that did I cover it all? Gold, silver, lead. Yeah, I think that sounds about right. So the RHIC is capable of accelerating all those different nuclei, sorry, up to 99.9996% the speed of light. So the center of mass energy is gigantic. It's
Right.
in the tera electron volt range, and it's huge.
Jeez.
All right. It's so basically you're able to collide those nuclei together, and that means the protons and the neutrons in each nuclei are smashing into their counterparts in the counterpropagating nuclei that's coming at it from the other side of the beam, and or proton against proton and whatnot. And oh, uranium! I just now remembered I was missing uranium. Uranium's another nuclei that they collide,
Got you.
and they
Got
do it without initiating an accidental chain reaction. Nuclear fission.
right.
It's
Right.
not in the. There's no way it can do a chain reaction. It's not in the right setup for that.
Got
Okay, so yes, uranium is another heavy nuclei or atomic nuclei that they or nucleus that they collide. Okay, so they're able to rip those neutrons and protons to shreds, or the protons in the hydrogen in the proton,
got
just the proton, which is the hydrogen ion, and out comes quark gluon plasmas. And to make a long story short, they've analyzed this to death from all different
right.
angles, all different features and aspects, and they realize that, oh my gosh, all the matter that composes us and galaxies, stars and planets and whatnot,
Right.
99% of it is vacuum energy.
Huh. Interesting.
It's the gluon vacuum energy. In other words, the gluon, all forces of nature, the fundamental forces, are a vacuum energy. They're a manifestation of the force's vacuum state. The force has a vacuum state, and that's what propagates the force. Is the vacuum state of the force. The photon in a vacuum state, the massive weak force bosons in a vacuum state, and the same thing with the quarks and the gluons. So they're in a vacuum state. So shockingly, only the quarks have a mass, just like the electron has a mass. But the gluons also, they don't have a mass. You don't measure. Actually, you guys, we don't measure mass. There's
Right.
no
Right.
experiments that measure mass.
Correct.
We only
Correct.
measure energy and use Einstein's E equals mc squared to calculate what the mass of that energy you're measuring
Right.
is.
Right.
Okay.
Right.
All
Yeah.
right. So to make a long story short, and I've already taken it long as it is, the result of the RHIC experiments with creating quark gluon plasmas is that the mass of all fundamental baryons. A baryon is the class of nucleons like protons and neutrons, and mesons like
Right.
pions and kaons. Baryons. So let's see. Okay, hang on a second. I overdid it. A baryon is strictly neutrons and protons, and maybe particles called hyperons, which are conglomerations or a bound proton and neutron with an exotic particle, which is a nucleon type particle of higher electric charge,
Got
doubly positive or doubly negative or whatnot.
right.
Okay, so that's what a baryon is. It's just basically the neutron and protons or an exotic version of those bound together. So so then you have the mesons. Well, the mesons and the baryons are two parts of the family of hadrons.
Right.
So hadrons are composed of the subfamily of baryons, subfamily of mesons. We don't need to worry about the mesons, but the protons and neutrons are what form the nuclei, which are the majority of the mass in all atoms on the periodic table, right?
Right.
Okay, all right. So the RHIC quark gluon plasma experiments demonstrated that the mass of all baryons is 99% gluon vacuum energy.
Oh,
The other 1% is just the quarks.
right. Wow. Wow.
So basically, we're made out of empty space.
Right. This does this take us, if I may ask, to the four vector potential, the notion that
No,
okay,
that's a separate question.
gotcha,
That's a
gotcha,
separate question. Okay,
gotcha.
so that's what I wanted to say. So if you want to modify, you don't speak of modifying inertia. That's a ridiculous thing to say.
Right.
It's like asking what the color of a smell is. Okay, how
Right.
about modifying mass? Can we modify mass? There's no principle for it, but the RHIC experiments give you the idea that if you can modify the condition of the quark gluon vacuum state,
Right.
then you can modify the mass of the baryon.
Got you. Got you.
But to do that, is a level of astronomical complication uh, that's beyond our capability to foresee or imagine at this time. You need to modify the quantum vacuum structure of all protons and neutrons,
Got you.
and the vacuum structure is the gluons. You need to do.
Got
We don't have a gluon technology yet.
Right,
And I
right.
said, yeah, I don't know if we will invent a gluon technology. You know why? The energies it takes to get to that vacuum state requires the RHIC. That means we're not going to have a tabletop or a Casimir cavity or some type of an experiment or even a simple laser to do that.
Right.
We have to accelerate a beam of two separate beams of heavy atom nuclei, or even just a couple, or even just a proton, in opposite directions. Have them collide into each other to create a gigantic center of mass energy to rip out the quarks and gluons from inside each nuclei,
Got you.
and or each nucleon, I should say, a nucleon being a proton and neutron.
Right.
And
Right.
a nucleon is another word for baryon. Sorry,
No
physicists
problem.
like to give a name to everything, literally.
No, no problem. Well, thank you so much for that in detail answer. The next question I wanted to ask, which is along the lines of, again, if something may be feasible or not, is with regards to negative energy. So, in your view, do you think that in either of our lifetimes we will see the experimental, I guess you could say, amplification of negative energy produced in the laboratory to a magnitude in which the negative energy can then be harnessed for something like propulsion?
Oh, I can't predict it. We're already producing uh, negative energy through the Casimir cavities
Right.
and squeeze states of light. That's
Right.
basically a modified laser beam, and that's described in my publications. It's described in other publications. Um, so basically, that's very feeble. The amount of negative energy you're pulling out of the undisturbed, you're disturbing the quantum vacuum.
Right.
A Casimir cavity disturbs the quantum vacuum by putting two parallel plates in the space, and so the vacuum that gets trapped between the plates is now modified.
Right. Right.
So the theoretical result of doing that is that the energy density of the vacuum state between the plates is negative, and
Right.
we have a precise empirical, or well, a precise theoretical calculation based on that, and we have all the experimental empirical evidence for it, but we haven't directly measured the energy density of the Casimir cavity vacuum state, or the Casimir vacuum state as we call it.
Got
That's because it's that's a whole other discussion. But we can measure the consequences of what does the negative vacuum energy state do. It creates an attractive force between the plates, and we've seen those plates collapse.
right.
Okay, now, squeeze states of light, it's an alternating pulse of positive energy density and negative energy light in the
Right.
laser beam. And the problem is, the way it works is that the negative energy density is much smaller in magnitude than the positive energy density is.
Right.
So that the net energy density of the beam is positive, which is what's predicted by um, Maxwell's equations as well as quantum electrodynamics. So, and quantum optics even. So uh, there's because it basically it more than averages out. You don't average it out to zero beam energy. Beams don't have zero energy. It averages out to a positive electromagnetic energy when you detect that beam with using a special detector.
So, in other words, you don't foresee a negative energy
I just
drop.
can't.
Right.
There. Okay. There's a proposal by Larry Ford and geez, and Fader. I don't remember his collaborator's first name. But Ford and Spader published 2 papers in the Physical Review on their proposal to use a parabolic cylindrical mirror
Right.
to focus quantum vacuum energies, or I'm sorry, to focus quantum vacuum fluctuations, the ZPF,
Right.
onto the focal line of the mirror. Now, what is that mirror? I just said parabolic cylindrical. What does that mean? Well, just if you're familiar with solar power, one type of solar power that's been invented and developed for since probably the 60s, maybe. What it is you use the parabolic cylindrical mirror. That's just a mirror that's got a parabolic shape, but you stretch it out along a long line. So the mirror is like a really, really long parabola.
Right.
Okay, it's really long,
Right.
and so when you shine a light at it, like sunlight, for example, outside, the light will be reflected based on the parabolic shape of the mirror onto what's called a focal line, not a focal point. Um, so you don't have a focal point, you have a line, because remember, the mirror is stretched out linearly.
Right.
It has a length, it has a finite length. So that
Right.
focal point becomes a line. See, a parabolic dish will focus light at a point,
Right.
right?
Right.
So that's the focal point of a parabolic dish, or a concave parabolic dish. So
Right.
this is the concave um, cylindrical parabolic dish. And it's not a dish really, but anyway. So cylinder means, remember what a cylinder is. It's like a can of
Right.
fruit, right?
Right.
And a can of fruit is round on its ends, but it's cylindrical between the ends.
Right.
So chop it in half, and you have a parabolic cylindrical lens or shape. So stretch it out to a long length, and what the light can be reflected by the mirror onto is a line, a focal line. Okay, so Ford and Spader, geometrically and quantum field theory wise, predicted that the quantum vacuum fluctuations will be reflected by that mirror onto the focal line. But it depends upon the angle of that parabola. If the parabola has a certain angle, then the then the ZPF, it will still be focused on the focal line, but there's some conditions there on what the range of that angle should be. If it's a certain range of degrees based on the shape of that parabola, then the 0 point fluctuations will focus on that line, and they will have a manifestly negative energy density. So the whole
Gotcha.
focal line will have negative energy density associated with those vacuum fluctuations. Now, the space outside of that focal line will have nothing but positive energy density of
Right.
ZPF. So the ZPF that's not focused on that focal line will have
Right.
positive energy density in the space outside of that focal line. Okay, then
Gotcha.
there's the alternative. Then there's another version. If the angle of the parabola has a different type of range and degrees, then you might have alternating negative and positive ZPF energy density along the focal line. So it's
Huh.
really weird. It just
Yeah.
depends upon how. So what is that angle? That's the bending angle. I'm talking about the bending angle of the parabola. So if you
Gotcha.
change the bending angle, you're going to have different effects. So I'm thinking, I've always been thinking, and I actually been publishing this since 2013, I think, or maybe even earlier, is actually probably since my 2009 book with Mark Millis, Frontiers of Propulsion Science,
Right.
by the AIAA Press. And the reprint, the corrected second edition, not the second edition, second printing in 2012. Um,
Which is a great book, by the way. For everyone that's watching, please take a look at that. Check that book out. It's fantastic.
yeah, thank you. Thank you for the pitch.
Oh, no
that's
problem. No
volume
problem.
that's volume 227 of Progress Series in Astronautics and Aeronautics of the American Institute of Aeronautics and Astronautics Press. And the title is Frontiers of Propulsion Science, with Mark Millis and I as the editors. And I've got 3 chapters in it. He's got 3 chapters, and then the rest of the 20. Let's see, we have 22 chapters altogether. So the other uh, uh, 20, the other eight, I guess 18 or 16, 16. So the other 16 chapters are by people in academia, industry, and U.S. government. So in any case, my expectation is that because the space of a cylindrical parabolic mirror, or parabolic cylindrical mirror,
Right.
is open-ended on one side of the mirror,
Right.
as opposed to the confined space between Casimir cavity walls or
Right.
plates,
Right. Right.
which in order to have a very large magnitude of negative vacuum energy, okay, let me give you a comparison.
Sure.
I did the calculation. In order to produce negative 10 to the, I don't remember what it is, somewhere in the ballpark of 10 to the 20th joules per cubic meter of energy density,
Right.
negative energy density. The plates of the Casimir cavity have to be 1/3 the Compton wavelength of an electron apart.
Ooh.
So if you look up what the Compton wavelength of an electron is, take 1/3 of that value, and that's how close those two plates have to be in order for the vacuum space in the space between the two to have a stupendous negative energy that will bend space-time, that will curve space-time so strongly that you can measure it,
Right.
that it
Right.
will have a measurable, observable effect on the space-time itself.
Right.
Okay, so we can't engineer that. No way. There's no way of doing it. Now look at the
Gotcha.
half space, the half open space, because remember the mirror is one boundary. The parabolic
Right.
cylindrical mirror, it's one boundary, not two. There's no two mirrors, it's just one mirror. And
Right.
that mirror is a parabola. And so that means the space away from that parabola, away from that mirror, that reflects and focuses sunlight or any kind of light or the 0 point fluctuation, it's all free space. And I'm thinking, well, all of that negative vacuum energy, given if you bend the mirror within the range of angles that is prescribed to get a manifestly negative vacuum energy of the ZPF along that are focused along that focal line,
Right.
then who's to say that we just can't scale that up somehow
Right.
and create higher magnitude of negative vacuum energy?
Right.
Or who's to say that we can intersect multiple focal lines together? So you have multiple mirrors with focal lines that have negative vacuum energy along the focal line, and so we intersect them together at a single spot and create a blob, a really super high magnitude negative energy. So that's something I've got a graduate student of mine at Baylor University working on for his PhD dissertation.
Wow.
So
Wow.
I think the answer is we can foresee some. This is one speculative hypothetical way of scaling up the magnitude of negative vacuum energy
Right.
using the parabolic cylindrical mirror and super radiance effects. Well, that's a very interesting effect. Zeldovich, the Russian physicist Zeldovich, um, predicted that you take a mirror ball, like a perfectly shiny conducting uh, ball of metal, or it's a mirror itself. The whole
Right.
ball is a mirror, and you
Right.
can construct that. A very highly polished metal will reflect, and you could get it. You could get the metal to have a reflective property that's almost perfect. Okay, if you spin it at half the speed of light, what it's going to do? It's going to be like I won't produce that analogy. I was thinking of an analogy, but even regular people won't know what the analogy is. So anyway, what it's going to do is it's going to literally grab the vacuum fluctuations surrounding it and drag them in the around the direction of rotation uh, of that spherical mirror.
Got you. Got you.
And the end result is that you've got incoming just standard vacuum fluctuations in the free space vacuum. There's nothing special about them, but that mirror is rotating at half the speed of light. It's going to grab those suckers and it's going to pull them around the ball until they come out as a coherent beam of 0 point fluctuations on the other end. And
Right.
that beam is called superradiance effect. And superradiance means it's going to have a stupendous amplitude of negative vacuum energy.
Got you. Well, thank you. Thank you for that insight. That's
Now,
very appreciated.
yeah. So now the question is, how do we accelerate a ball like that half the speed of light?
Right.
So,
Right. Right.
so you've got these, so you've got these issues that you have to overcome with the technology to try to implement these ideas. They're still yet to be discovered technologies. I mean,
Right.
we haven't explored the full phase space of quantum field theory to figure out how we can produce manifestly negative blobs or regions or beams of negative energy. In fact, Burrell and Davies in their pioneering book on quantum field theory and curved space, which was published in the early 1970s, they predicted from quantum field theory that if you just take a single mirror a reflecting mirror, and you accelerate it rapidly, where the rate of change of acceleration is actually high. So it's not a constant acceleration; it's a changing acceleration. So
Right.
what that does is that it's going to ram into the vacuum fluctuations of free space, and what that's going to do is cause those fluctuations to bounce back off the mirror, and they bounce in the direction travel of the mirror, direction of acceleration of the mirror.
Got you.
And what they found out is that what happens is that mirror is parametrically exciting those vacuum fluctuations. And the parametric excitation acts to cohere the reflected fluctuations into a beam that moves in the same direction of travel as the mirror. But the energy density of the fluctuations is all negative. There's no
Right.
positive in it. It's all negative. So there's a beam, but we don't know how to do that. The the amount of acceleration required to do that is stupendous.
Right.
It might even be I can't think of what a number is. Um, it,
No
it's
problem.
just a huge number. Yeah, it's something we
Yeah.
can't engineer. Yeah.
Got you. Well, with
So
that,
we
yeah.
that's the limited things that have been done. We need more people doing these kind of studies to look at other conditions, other circumstances, invent them in their imagination, put them into the equations, and find out if it's anything that we could engineer and do. So
Got you. Well, thank you. Again, thank you so much for that. The next question, one of the last few questions left that I did want to ask you is, so you've done an incredible amount of research into wormholes to the point where
and
many
and warp drives.
and warp drives, yes, to the point where many people say that you are, in fact, the world's foremost expert on both wormholes, warp drives, and general relativity. Could you be so kind as to break down the various types of wormholes that general relativity would permit theoretically?
Okay, well, I appreciate that people think of me that way, but it's not true. The foremost expert is Matt Visser and
Got
his collaborators, Francisco Lobo and Carlo Orvelli,
got
and there's a few other names out there, not too many of them, but they're the ones that did all the pioneering publications on it, and I picked it up as I applied it to faster than light propulsion physics. These guys did the fundamental theory work on those topics. So basically, well, there's a whole topology of traversable wormholes. As a matter of fact, there's a taxonomy of them.
Oh,
And almost the same thing with warp drive, but a taxonomy of wormhole means you've got static wormholes, which
right,
means they don't change in time. You
right,
create them and they stay the same. You turn it on or you can turn it off. Okay. Now that subdivides into a taxonomy of what's the shape of the throat. So you have all kinds of different wormhole throat shapes. They could be spherical. They could be like a stargate, a plane. They
right.
could be dodecahedral, tetrahedral, um, and so forth. I can't think of the other ones, but
Sure,
there's a
sure.
whole bunch of different shapes of traversable wormhole throat, which Matt Visser identified and published in his book Lorentzian Traversable Wormholes from Einstein to Hawking in the AIP Press, 1995. And that's a great traversable wormhole monograph. Then the other part of the wormholes is you start. So you have the dynamic, then you have the you have the static. Now you have the dynamic wormholes. The dynamic wormholes just mean that they change in time.
Gotcha.
Okay, so they have a property such that they're not constant or static with time. They change. They either increase in size or decrease in size. That type of thing.
Gotcha.
Okay, but they will have the same taxonomy of throat shapes.
Gotcha.
Okay, and then you have wormholes that could be specifically designed to work as time machines. So
Right.
there's your type of wormholes.
Right. Okay. Got you. Wow. Interesting. Thank you. That's very intriguing. The next thing I did want to ask was that a lot of people that I've personally interacted without mentioning names seem to have a misunderstanding or don't understand whatsoever that, again, please correct me if I'm wrong here, but that the four vector potential is in fact more fundamental than the actual fields themselves or give rise to them. We see this through things like the Aronoff-Bohm effect, and we know, for example, Konoplinsky wrote a very nice paper on how the electromagnetic vector potential is intuitively more foundational than even the E and B fields, respectively. Could you please explain to the audience the implications of what this means? And again, to the audience, we're talking about field-free potentials here, which may seem
No,
counterintuitive.
no, no.
Or
There's no
sorry.
such thing as the field-free
Oh,
potential.
sorry,
If
sorry.
it's field-free, the potential doesn't
Doesn't
exist.
exist.
I would like to clarify that what I was referring to when stating field free EM potentials was this paper in particular out of the Soviet Union, in which at the time of the recording Dr. Davis was not aware of. Now, Dr. Davis found that when examining the paper, the authors meant that the E and B fields were field free with a non zero A field. And so one can make a very strong argument that a free field potentials may not exactly be the best way to adequately address what we were discussing in our conversation.
Sorry, my apologies. Sorry.
Yeah.
If you could please explain to the audience what potentials are in this regard, the four vector potential in relation to a matter and physical fields.
Okay. Well, Maxwell uh, assembled his equations for electrodynamics on the principle of Faraday's work, Ampere's work, and et cetera, Hertz and so forth, those guys. So he put together Ampere's law, Gauss's law, blah, blah. So he got all the equations of electrodynamics, and you can contract those or collapse them into a couple of tensor equations. So there's like four of those equations originally, and collapse them into two tensor equations. And so to make it more compact mathematically in appearance. Okay, so those equations are based on the discovery of electric fields and magnetic fields, static fields, through a variety of experiments that Faraday did and Ampere and all the other folks did back in the 19th century. Okay, then they came upon the discovery of moving fields, propagating field. And what they discovered was you don't have a propagating electric field, you don't have a propagating magnetic field, you have a propagating electromagnetic field that's unified. So, okay, so Maxwell's equations are constructed on the back of the measurable, detectable electric and magnetic fields. Okay, so you talk about how those fields are created by electric charges, moving electric charges, and a moving electric charge is also another word for current, electric currents. Okay. Okay. So from that, he made the discovery of tinkering with the mathematics and the identity properties of vector calculus, because you have to take a vector cross another vector using the cross product rule, or a vector dot another vector using the dot product rule. And he's looking at these identities that go along with calculating his equations, and boom, he discovers the propagating electromagnetic radiation out of that. And okay, so yeah, we can work with that. That was the fundamental basis for the discovery of radio. Okay, and okay, all right. Now, fast forward to quantum theory popping up. So, well, okay, we have quantum theory popping up a few decades later, and then I think it was Dirac who relativized Schrodinger's equation, or the equation. There's two types. There's Heisenberg or Schrodinger's equations for quantum mechanics. One or the other. You could use your choice. Take your choice.
Right.
Well, that's classical physics. In other words, classical time, classical space, nothing special. But when you get into the relativistic regime of electric charges moving, all of a sudden things go crazy and haywire with Maxwell's equations. Now you discover, oh, I need to make Maxwell's equations relativistic. And it turned out Maxwell's equations were already relativistic. They already incorporated the properties of relativistic motion in the equations. But in any case, so we've got that pinned down now. Now fast forward to quantum field theory. So Feynman and Wheeler decide we need to quantize electrodynamics, because we're now been experimenting with electric charges for so long. We're seeing all kinds of new phenomenon associated with that go beyond Maxwell's equation. We're looking at stuff at the quantum level, and Maxwell's equations doesn't work at the quantum level. Those equations break down. So we have to have a quantum description of electromagnetic radiation, electric fields, and magnetic fields. And so they go through the motions, they develop quantum electrodynamics. Okay, well, to create quantum electrodynamics, what you need is a field, because that's what the electric and magnetic fields are. They're a field.
Right.
They're a vector force that propagates through space. Well, I said that electric and magnetic fields don't propagate through space. What I meant is they don't propagate like a wave. You'll
Right.
have a static electric field lines and static magnetic field lines in space, right?
Right.
Correct? Okay.
Right.
Well, those static field lines don't move. You can make them move if you mechanically move the electric charges or the currents, right? Or the
Right.
magnets even. Okay.
Right. Right.
Those will move. And remember, Maxwell discovered, hey, if you change your magnetic field with respect to time, you're going to create what was it? My gosh, my basic physics is bad. But a time rate of change of an electric field, I think, produces a magnetic effect and vice versa.
Right.
Right?
Right.
I think actually, isn't it a spatial variation of the magnetic field or the electric?
I think it's
I don't.
a spatial variation.
Yeah, because I don't have the damn book in front of me. If I had the book, I'd be able to tell you.
No
So
problem.
I
No
just
problem.
can't remember it. I can't remember it off the top of my head. So right now, I know a spatial variation of one of those fields gives the other field, and a time variation of the other field gives the previous field. So just
Right.
vice versa. Well, okay. So now we got to get to the quantum level. So the quantum level is what's the field? What are these fields? And we imagine that they have to propagate.
Right.
So they invented a field of massless harmonic oscillators. So so it's like, think of a grid pattern. Well, how about this? Think of balls. They're electrically charged and they're coupled by a spring.
Right. Right.
Now make a bed mattress of that, which looks like a field. And it
Right.
goes off to infinity. So your bed mattress in area has an infinite area. It goes off in the X and Y direction. In reality, it goes off X, Y, and Z direction in an infinite volume of space. But I wanted to make this easier by looking at it in terms of a plane.
Sure. Thank you, sir.
So every electrically charged ball has no mass and it has no size. We'll call it an infinitesimal point. So the ball is really an infinitesimal massless point. So it's coupled to the one next to it at some distance by a spring. And what do these things do? They just, springs get stretched and compressed so the charged balls are oscillating.
Right. Right.
Okay, so you got a field of oscillating electric charges coupled to each other across an infinite field in space.
Got you. Yep.
Okay, so how do we describe that mathematically as a quantum field? All right, so I'm going to skip a lot of the work
Sure.
here, the math, and go right to the throat. The throat is, I'm going to grab the throat, and I'm going to say they had to invent the vector potential.
Right.
Now, the vector potential was already known by Maxwell. It was a gauging condition that he used on his equations for the time and space varying electric and magnetic fields. And so when you apply a derivative to the vector potential, it should give you zero. So it means you could add it to the electric and magnetic field equations, and you won't have any consequence to the end result. You'll get the same end result as if you didn't have them. So I'm kind of doing a really poor description of it, but this is the best way I can. Not having reviewed my undergraduate and graduate electrodynamics. Okay, so they created the vector potential as a classical field, but Maxwell and his contemporaries and their younger generations that followed, or newer generations that followed them, insisted that this was an auxiliary field. The vector potential was, and it is fictional. The only thing you can measure are electric fields, magnetic fields. But this nice vector potential is not measurable. It's not physical.
Right.
And that's what they taught electrical engineers for decades.
Right.
Okay. So what is the vector potential? Well, the vector potential has two components. It has a scalar component, which is called the scalar potential, and it has a vector potential using that same word,
right,
which represents the three spatial directions of the vector potential, AX, AY, AZ, where A is the spatial component of the vector potential. The scalar potential that I mentioned earlier is called A0. And in relativistic mechanics, space-time distances are unified. So you don't have independent time, independent space. Now you have space time, and you can make a 4-vector that
Right.
represents an event in space time, a point. A point in unified space time is an event.
Right.
Why is that? Because you write a little parentheses, and the first component of that vector, of that event vector, is time. Then the following component is x, y, and z, the 3 coordinates of physical space. Or if you're using cylindrical coordinates, it'll be rho, z, phi, where rho is the radial direction, z is the vertical direction, and phi is the azimuthal direction around the cylinder. Those are
Right.
cylindrical coordinates. And if you use spherical coordinates, it'll be r, theta, phi. So the radius to the surface of the sphere, theta is the cotangent angle, and phi is the azimuth angle around the axis of the sphere. Okay, so whatever coordinate system you use, you're going to have 3 spatial dimensions of the of an event vector, a space-time event vector. So
Right.
it'll be time and some 3 components of spatial direction. Well, the same thing is true for electric fields and magnetic fields and for the vector potential. And in fact, there's no time component of the electric or magnetic field. Those are 0. You only have EX, EY, and EZ. You
Right.
have BX, BY, and BZ for the electric E and the magnetic B fields. The
Right.
vector potential is more fundamental because it's like an event point in space-time. It's going to have a time component, which is the scalar potential phi, and then it's going to have the 3 A components in the 3 directions of space. AX, AY, AZ, or A1, A2, A3, where 1, 2, and 3 could be any coordinate system you choose in 3-dimensional space.
I find
All
that
right.
super cool, by the way. Yeah.
Yeah. Okay. So you do the mathematics on the quantum excitation of your harmonic oscillators. You're giving them energy, or you're taking energy away.
Right.
And when you do that, you're describing the nature of what's called creation and annihilation operators
Right.
on the modes of vibrations of those massless infinitesimal quantum charges, which are bouncing around in the field. They're coupled to the other ones. What is the coupling? That's the force. That's the fundamental force. That's
Right.
what the spring represents. And I'm sorry, I neglected that. So the spring
Oh,
represents the fundamental force of interaction between 2 adjacent or 3 adjacent or an infinite number of adjacent charged massless points,
points. Right.
or I should say points of massless electric charges. There you go. That might be the better way of saying it.
Sure.
Okay, so the electromagnetic force is to be imagined as a spring acting between 2 adjacent or multiply adjacent massless electric charges of 0 dimension. They don't have a size. Okay, so describe the energy excitation and the creation of energy excitation and the destruction of energy, or the de-excitation, I should say, really, of those point charges. They had to invent the vector potential, the 4-vector potential. 4 meaning the 4 components of the Maxwell vector potential. The scalar field being the time component, and then the 3 spatial components. And that was labeled A. So the 4-vector potential is labeled A, and it's going to be equal to, in parentheses, phi, comma, and A1, A2, A3, and you could choose whatever 1, 2, and 3 are based on what coordinate system you want to use for your space.
Right.
Okay, so they figured out, we've got to quantize that A field. So they quantized the A field using the procedures of quantum mechanics, and now you've got a description where everything you've been describing in terms of electromagnetic radiation production or destruction, or I should say emission and absorption,
Right.
is described not in terms of the electric and magnetic field, or the electromagnetic field. It's in terms of the vector potential, the
Right.
4-vector potential.
Right.
So that's more fundamental. And from the 4-vector potential, it was shown that you can define the electric field as a combination of the spatial and time variation of A. And then if you use a different time and spatial variation, it's either using the scalar product of 2 vectors or the cross product with the time derivative component added on. You can define the magnetic field. And then if you throw those into the Maxwell equations, you get the wave equations for A. So A can propagate through space-time. And so this was all discovered from quantum field theory. And I'm sorry about that. I'm trying to move. I'm holding my phone. I don't have a laptop with the webcam on it.
One more question after this, then we're done. So no, thank you.
Yeah. So let me wrap that up. So basically, that's the fundamental field from which the electric and magnetic fields can be derived, and it's the fundamental field from which the quantum chromodynamic field is derived. It's the fundamental field from which the electroweak field is derived, and so everything can be reduced down to the 4-vector potential, and everybody kept going, both in physics and electronic electrical engineering courses, saying that's not a measurable field. It's a mathematical device to help make the calculations of Maxwell's equations simpler, easier to do.
Right.
But the fact is that Aharonov and Bohm predicted that you can measure it.
Because if the classic, just to clarify, if the classical electrical engineers and all that were saying it was just a mathematical construct, if they were right, then that means the Aharonov-Bohm experiment would not have worked.
That's correct.
Right.
So they were wrong. They were all wrong because Aharonov and Bohm proved that if you shoot two beams of electrons, one on one side, one on the other side of a magnetic solenoid, where current is moving in a solenoid. And what does the mathematics for Maxwell's equations say about where the magnetic field is? The magnetic field is confined inside the solenoid.
Inside, right.
So therefore, the prediction is the two beams on each side of the solenoid should go in a straight trajectory from where they're emitted to where they end up going off into infinity, or maybe they hit a wall on the other side.
Right.
Okay, well, that's not what happened.
Right.
What happened is, if you put a screen on the other side, on the back side of the solenoid, you found that the two electron beams created an interference pattern. Why? Because they were bent. Oh my God, you're saying that the electron beams on either side of the solenoid were bent around? Their trajectory was altered? Well, if there's no magnetic field, then what the hell alters the trajectory? Well, if you do the quantum calculation using the vector potential field, you will find that coupled to the wave function of the electrons in the beam, in each beam. So all the electrons in a beam have a wave function to describe their propagation in the beam around the solenoid, even in free space with nothing there. So you write the wave function for each electron in each beam, and what you find out is that the construction of the solenoid with the current going in a helical winding or solenoidal winding, actually, yes, the magnetic field is restricted to the inside of the winding.
Right.
So there's no external B field in coupling to the electrons, thus influencing their trajectory. Instead, the calculation shows that the vector potential is non-zero outside of that solenoid. Outside of that solenoid, the 4-vector potential propagates forever, or it's not propagating as a radiation. It's out there forever in all different directions. And so it turns out that the wave function of the electrons in each of the two beams are coupled to the vector potential. That coupling changes the phase of the electron's wave function. That phase, it's a phase shift, or called the Berry phase in modern lingo. So that change in phase of each of the electron in each of the two beams causes them to bend around the solenoid and strike a screen and create an interference pattern.
That is incredible. Could we say that the magnitude of the 4-vector potential is arguably infinite in space, or no?
Yeah, electric fields are infinite, magnetic fields are infinite. They fall off with the 1/r dependence. I mean, electric fields fall off with 1/r squared. Magnetic fields, depending on the geometry, they usually fall off as 1/r cubed. And the vector potential, interestingly enough, so I made a misstatement, but only for clarification. So yes, if you work the vector potential through Maxwell's equation, you can get a propagating vector potential radiation.
Got you. Right.
It will, the vector potential A, the 4-vector potential A will obey a wave motion equation. It's a second-order partial differential equation, the wave equation. It will obey the wave equation, which means the vector potential can propagate through space-time as a radiation. I was speaking in terms of just the static vector potential created by the current in the solenoid. The current is electrical current is moving through the solenoid and it's creating a static A field outside of the solenoid. So that's what's static. Okay,
Right.
and it has a distance dependence in strength. It will fall off, but
Right.
you can propagate it through space as a separate radiation, just like the electric field, just like the magnetic field. Why? Because if you replace if you replace the electric field in its wave equation with the definition of the electric field in terms of the vector potential, you'll get a propagating vector potential. And the same thing with the magnetic field component. If you do it that way, strip out the B, replace it with the B's definition in terms of A, you'll
Right.
get the radiation of A. So
Amazing. Well, I just want to say first off, we're coming up to or to end. We're coming up to almost 2 hours at this point. I want to thank you so much for your time.
so how, do you have
Oh,
any other
sorry.
questions?
One final question I did want to ask.
Okay.
This is more just for the people that are more interested in my audience, within my audience regarding UAP crash recovery and all of that, relative to what you could speak on. So, putting private contractors aside for a moment, is there any agency that you know of in which you can comment on that would be likely to hold the most amount of UAP recovered vehicles or material? For instance, would the DOE have more access or have within their possession more material or biologics or information compared to the DIA or the NSA or the CIA, or
Okay.
does it depend, or is there an overlap?
Okay.
Yeah.
Okay. That isn't how it works.
Okay.
How it works is that there is a intelligence agency owner of the crash retrieval portfolio.
Got you. Okay.
The executive agency that carries, now see, the intelligence agency only has a science and technology directorate that handles spy technology development
Got
or the reverse engineering of enemy spies technology.
you.
Okay.
Got you.
Okay. So they're limited. They're limited in what they can do.
Right.
So what they do is they go to an executive agent that handles all of the laboratory work for them.
Got
And
you.
that would be Department of Defense elements. So it's
Got you.
not that one agency has more than another. It's that one agency owns it all and delegates the work to the Department of Defense. And
Got
the
you.
Department of Defense delegates that work to the private contractors, because when Bush was president during the 2000s, he said, we're going to commercialize government. We're going to turn, government more into a business operation. So the consequence of that is we're going to remove science from a lot of our DoD agencies.
Ah, right, right,
I mean,
right,
we have the Air Force Research Lab, that's science. We have the Army Research Lab and the Naval Research Lab. Those are science, right?
right,
But
right,
that's it. But those
right,
are for specific mission purposes or application.
right.
This type of thing is a lot more different than those.
Got you.
So it'll be a glom of Department of Energy labs, military, maybe some military labs, but generally security is better and is harder. And well, first of all these laboratories are subject to FOIA.
Right, 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 right. Yeah.
But so if you hand it off to corporate America, corporate America is not subject to FOIA
Right.
because that's the private enterprise. And not only that, they have judicially tested proprietary protection laws for their intellectual property. Any work that they do on a defense or intelligence agency contract that invents something new, that's intellectual property that they own. Now the government paid for it, so the government doesn't get into profit sharing. It's how the government agrees with the company to share the IP in general.
Gotcha.
Now the government could be a patent holder, but so will be the private company guy. So they will both be they'll be both the patent holders,
Gotcha.
co-patent holders on an invention made
Right.
by the industry guy. Because the
Gotcha.
government paid for it, the industry guy invented it. So
Right.
you'll see both government and industry names on a patent.
Right.
So that's how
Gotcha.
that works.
Thank you so much, Dr. Davis, for coming on the show. It's been an absolute pleasure to have you here for almost 2 hours. I know we planned for only about an hour or so, but I want to thank you for extending your gracious time for being here. And again, to the audience, please, I know that a lot of you out there may not fully understand the depth of the science that Dr. Davis went into, but I encourage you to listen or watch this conversation again over and over so that you can try and understand in a more comprehensive manner what Dr. Davis is saying, because he is one of the most highly respected physicists out there that I know of. So, Dr. Davis, thank you so much for coming on, and hopefully you'll come back at some point if you would ever like to.
Yeah, thank you for having me on. I was happy to be on this interview with you and answer all of your questions. And thank you very much.
Thank you. Take care.
Bye-bye.